Okay. I believe we are live now. We're recording. This is for the Thermochem retake. So this is the review. So having just come out of spring break, and I think that everyone's probably a little bit tired, and I don't expect a lot of people, which is fine. So this is almost like a screencast. I'm hoping people will show up and have questions. In the meantime, though, I'm going to go through some questions I've already populated in the Q&A section. We'll start off with a simple one. What are the different ways to solve for enthalpy, which is delta H? And some of that ties in to other questions, but we'll just start with a simple one. Let me switch to my bamboo paper. Excellent. Okay. Oh, I should change the ink on this, huh? Size anyhow. So, delta H. And so, one way to do it is Hess's law. Another way to do it is to do the delta H of formations. You add them all together, and you get the delta H of the reaction. And you can also, sometimes you can, given the delta H of the reaction, which for some reason happens to quite often be the delta H of combustion, you can find the delta H of formation. Another way could be doing delta H's with bond energies, or bond enthalpies. Energies are enthalpies. And so that's a little bit different, and there's a way to do that. And I'll open up that question a little bit later. And the last way is probably the most frequent, or I think the easiest way, and that's one that can be used. It can be used, and it's actually kind of, I guess actually, what am I saying? That's actually number 2. What's the fourth one? Oh, come back here. Sorry. This one is I guess that's the more frequent one. If you're finding the delta H of the reaction, and it's usually the delta H naught. It's the sum of the number of moles times the delta H of formation of the products minus all that for the reactants. We'll get to that later. I'm doing too much here. So Hess's law, the delta H of formation and the delta H of reaction. You have the delta H from bond energies. And gosh, I feel like there's another one besides this. Well, delta G is equal to delta H minus T delta S. Okay, so there's a delta H in there. So there's a few different ways you can find the delta H. And I would say that you're going to do all 4 of these on the test. With Hess's law, don't forget, and I think a lot of people are pretty good with this. I think it's probably the easiest actually of the group. I think this is the most common. Number 2 is the most common. I think number 1 is the easiest. Hess's law that, so for a reaction, you have, if you reverse the reaction, you have to reverse the sign on the delta H. And if you multiply or divide, then you also have to multiply or divide. If you do that to the reaction, you have to do the same thing, multiply or divide the delta H. And then at the end, you add all the delta H's together. So that's a pretty good one. The delta H of formation and the delta H of reaction, that's a different question. I'll get to that one later. Delta H of bond energy. I don't know if I made that a question, but I can always, we can definitely talk about that one later. Oh, I did have it as a question. And then finally, the delta G equals delta H, and that one's another question as well. So I'll wait to get to those questions until later. I see that we've got some questions, some people came in. So I'm gonna go ahead and start answering some questions. So let's see. The first question that I see there is from Mary. Could you please review free response number 1A on the actual test? We can do that. All right, and so all right. Good, all right, so we're going to number 1A. Not a problem. And let's see. Oh, as I happen to glance off, it says, Mr. Warner, do you know how to turn off safety mode off because it won't let me watch the video? Let me address that one really quick. All right. So let's see if I can share my own entire screen. All right. That's a little crazy. I think that when you're doing this, Aria, you might actually, let me take a look for a second. You might need to, if you're doing this, I don't know if you're viewing it like in YouTube, or let me see if I can view it with my own. Well, maybe you probably just followed the event page, is what you probably did. So I don't know. So there's the event page, and let's see if it'll let me do it because I'm already there. It's in YouTube. Okay. So probably, you know what, I'm gonna close this out because I'm being a little crazy. If you go into YouTube and you are, if you go to the very bottom of YouTube down here, this is where you can turn safety mode on or safety mode off down here. And I'm hoping you can see that on my screen. So down here at the bottom. I don't know how to make this bigger right now. Let's see if I can. So if you scroll all the way to the bottom, there's this section right here, English Worldwide Safety On and Off. You need to click that, and that's going to be your, you just do the drop down arrow and it gives you the options. It probably is, you can turn it to off. Mine safety says it's on, which is good. But if you turn it off to disable it, I don't know why it's causing that problem. Let me see if I can see what happens if I can scroll down again. I'm trying to save it for off, and I wonder if, because of our domain, it's stopping it. That's weird. Especially because we're in the same, I don't know how to do that. That's really odd. Well, somehow you got a question in there. So if you, you put a question and I don't know how to respond to that question besides just talking. So if you're just talking about this video, I don't know what to tell you about that. When I put it in YouTube, it should be fine to watch with whatever, but I'm not sure right now. That's interesting. I can't seem to turn my safety mode off. I can't remember the last time I got stopped on a video though, and especially one within a domain. So I'm a little confused. I don't know what to tell you. I'll have to take a look at it later. Right now, it's a little hard to do because I don't want to spend a lot of time on it. I want to address the questions. So if you have any questions, how about this? Email it, and I'll keep checking my email. Again, I don't know if you're getting any of this. Okay. 1A. All right. For response 1A. It was actually a really straightforward question. It just feels weird. So if you're burning 2 grams, so you have 2.00 grams of the phenol. I was going to do it on my thing. I don't think it's not a good use of time to put on there on the bamboo paper. 2 grams of the phenol, okay, and it's burned, and you get this much kilojoules. And the question is, calculate the molar heat, right? Well, if you got that much out of 2 grams, well, that's that much per how many moles, basically. So you take 2 grams and divide it by the 94.113, which is the molar mass of phenol. So you do 2 divided by that, and that gives you the number of moles. And then it's 64.98 kilojoules divided by that number of moles. And so that gave you the -3058. You'll see one of those questions again on the retake as well. You just have to take however many grams there are and divide it by the molar mass to get the moles, and however much was burned divided by the number of moles, that gives you kilojoules per mole. So that's all that question was. So hopefully that was helpful. Okay. This is the question I asked or answered. I just selected Aria's question again. Mr. Warner, how do you turn off the safety mode? I tried to do it, and apparently I could do it. So if you go back in the video, you can see where to do it. I don't know why it won't let me do it. Maybe it's because I'm in the middle of a Hangout right now. I'm going to check my email. Maybe I'll send Aria a quick email. Okay. All right. So at this moment, we don't have any other questions up there. So I'm going to go on with the next thing. I talked about Hess's law. The next thing is how are enthalpy, formation, reaction, and combustion related? And so I'm going to go back to my bamboo paper for this. And we'll take a look at so this one is so delta H of formation, delta H of reaction, and delta H of combustion. It's a horrible looking triangle for delta. Okay, so the whole equation is that it's really the delta H of the reaction is equal to, I think I wrote it wrong on the other page now that I think about it. I think I put a delta in front. Yeah, there's no delta right here. I mean, no sigma, not the delta. There is a delta there, not a sigma. Okay, delta of the reaction is equal to the sum of the moles, the number of moles from the coefficient, times the delta H naught of formation of the products, minus the sum of the number of moles times the delta H of formation, delta H naught of formation of the reactants. And these are coefficients from balanced equation. Okay, so if we had a, like the phenol, I think that was a combustion one. Let's take a look real quick. Yeah. So if I have this C6H5OH plus 7 O2s yields 6 CO2s plus 3 H2Os. And what's happening here is that the delta H of this reaction is the same as the delta H, same thing, delta H of the combustion. They're the same thing here. This is a combustion reaction. They're the same thing. So really, this is interchangeable when you're talking about this. It's also like the square is a rectangle, but a rectangle isn't a square. Like a reaction is just a general reaction is a combustion reaction, but all combustion reactions are not all reactions. Like there's other types of reactions. So anyways, that's how they all fit together. Now, what you'll see quite frequently is maybe an easy one will say, hey, what's the delta H of this reaction? But quite frequently, it'll say, hey, what is the, let me change colors on this. What is it for this? And that was actually, you could see that in, and we'll go back and take a look at it right now in the practice, or not the practice, the actual test. That was a major part, question, I'm sorry, on the test. So let me pull it up. I have a very hard time doing one thing at a time. Okay, so you can see on number 1B, the delta H of combustion, which is the delta H of reaction, right? Same thing. Let me make it a little bigger. Okay, delta H of combustion, which is the delta H of reaction, equals the sum of, and there should be an N here and an N there. But anyways, the delta H of formation of the products minus the delta H of formation of the reactants. Now, this negative 393.5, that corresponds to the CO2, which is a product. And you have 6 times that, so that's a product. You have the 3 times the negative 285.85, that's the water. That's one of the products. At minus, and then reactants, X plus 0. The X is the phenol. Okay, it wants to know the heat formation of the phenol. X plus 0. Now it's 0 because at standard state, room temperature, and an element in its standard state is going to be 0. So any of the elements that are Brinkel-Hoff have to be diatomic, but they end up being 0, and so then you just solve for X. And this negative 3,058 kilojoules per mole, you already calculated the kilojoules per mole from 1A. And that's the answer, because that's the delta H of combustion of that per mole. That's what it is. That's why it goes in there. That's why that number goes in there, not the actual amount that was given from 2 grams, because that'll change every single time, right? Well, what if we had 3 grams? What if we had 4 grams? That's why you can't use that number, which in this case is like what was it, 64.98. You can't use that because it changes, but the negative 3,058 kilojoules per mole doesn't change. That's where it is at 25 degrees Celsius. And solve for it. So that's how delta H of formation, delta H of reaction, delta H of combustion are all related. Okay, and now we have another question. Aria, could you do number 3 on the free response on the test? So let's take a look at that one. Let me make this a little bit smaller so we can get the whole. Oh, this is a bond energy one. So I'm going to do this, and then at the end, I'm going to talk about bond energies. I'm going to just refer back. Okay, so it says use the table of bond energies below to calculate the enthalpy change, which is delta H for the reaction below. Now we have this is the formation of water from the elements in their standard state, which if we were just doing the delta H, this would be, we would have to just have it, right? You have to, since H and hydrogen and oxygen are both in their standard state, they would both be 0, and you just have to get water, but that's not what's happening here. We're doing it from bond energies, and you need to use the number of moles. So it's the sum of the bond energies that are broken. So the ones that are broken are the hydrogen and oxygen, and you have to multiply each of those bond energies times their coefficient. So you have H and H. You have H2 and H2. You have 2 H2, 836 kilojoules per mole bond energy between the two H's. So that's why it's 2 times 436. The oxygen is a double bond, O double bond to O, which is why that's a 499. Those are the bonds that are broken. Now you have to subtract that, or from that, you have to subtract the bonds that are formed, and the water is formed. And when you get water, you have 2 OH bonds in each water. Okay, so you have 2 OH bonds in each water, which is why there's that 2 times 460. But then there are 2 water molecules, so you have to multiply the whole thing times 2 again. So it's 2 times 2 times 460. So once you do this math problem, you get the negative 469 kilojoules per mole. I believe there will be one problem like that on the test. I'm trying to remember if I think it's a free response problem. It might be there. I don't know if I have it there, but that's how you would solve for bond energies. Okay. Pretty straightforward. All right. So, and that was one of my other questions. So I'm going to select that one and just say, hey, make sure you look back in the last 5 minutes. I answer that. Okay. Arya has another question. Multiple choice number 5 on the test. So let's scoot on up to multiple choice number 5. Oh, another bond energy. So makes sense. So why don't I show the work for this one? I'm assuming you have the test in front of you. We know the answer is going to be C because it says C, but let's see how that works. Ha ha ha. Not that funny, I get it, but I just happen to be saying it already. Okay. All right, so I'm going to scoot over to another problem. We're going to say multiple choice number 5. And I'm going to go to blue. Actually, I like the dark blue. Okay, so we've got N2 plus O2 yields 2NO. And it's bonds broken, so you're getting, to get the delta H of the reaction, you have to get the sum of the coefficient times the bond energies that are broken. Oh, my handwriting is terrible. On energies from the ones that are broken minus the sum, the coefficients times the bond energies that are formed. So this one's that weird one because these are reactants in front, which doesn't usually happen that way, and it's products at the back. So when we do this, we have the ones that are broken. So we've got an N triple bond N, which is 941 kilojoules, plus O2, which is an O double bond O, just like last time. So that's a 495 kilojoules, minus, and then we have an NO, and there's only one option for that. That's the 607. And the number, the coefficient is 2 times 607. And kilojoules. So without using a calculator, okay, 2 times 607 is going to be about 1200. And this is about 500. And this is about whatever, 940. So if we said that's 1440 minus 1200, then it's about 240 is what I would do. And I'd say, oh, C, kilojoules. Now there's a D option that says D is equal to 301, but C is equal to 222. And I rounded down here. So I had an extra 14, take off there, and I rounded up and whatever else. So I think that this is the 240 is closer to this. It does not equal the D. So that's why I picked C. So that is multiple choice number 5. Again, it's no calculator, so it's no fun, but you can just do some rounding and get pretty close to where you need to be. Okay. So that was that one. Okay. The next question that I want to do is the Gibbs free energy, enthalpy, and entropy. How are they all related? And I'm going to continue on my sheet here. And we have delta G, which is Gibbs free energy, is equal to delta H minus T delta S. Okay, so you can solve for these in several different ways. Sometimes you're solving for delta G, so you're leaving it as is. Sometimes you're solving for delta H. Delta H is equal to delta G plus T delta S. So you solve for that. Sometimes you're solving for delta S. Delta S is equal to delta H minus delta G all divided by T. And sometimes you're solving for temperature. So in this case, we have delta H minus delta G over delta S. In this situation, most often what happens is they're looking for that crossover temperature. So where does it go from being spontaneous to not spontaneous? So when you're dealing with a crossover temperature, then delta G is equal to 0. So then temperature is equal to delta H over delta S. So you have to be able to manipulate those equations and look for how you have, where you have these other values in your problem. Now, if you're missing one of those values, maybe they gave you enough other data that you could figure it out. Maybe you have to do the sum of way of getting because you can do that for delta G, you can do the sum of to get delta H, and you can do the sum of, my handwriting is awful, delta S. So there's lots of different ways that you can get those. And actually, I'm going to have a sample problem here in a little while, and I'll show you. I want to get through some of the basic questions first, but that is definitely one way to approach it. Okay. And so Aria has another question, multiple choice number 7. Okay. Let's take a look at that problem. All right, number 7. So which of the following reactions has the largest positive value of delta S per mole of CO2? So delta S is entropy. The larger the positive value, the more entropy, the more disorder, the more randomness you're dealing with. You want to, if you're increasing delta S, you are becoming less ordered. You have smaller molecules. You are moving towards gases, away from solids, liquids, and aqueous. You're having more molecules. You're going from fewer to more molecules. Those are all ways that you can get a more positive value of delta S. So I look at these, and H2 plus Cl2, they're gases, going to a more ordered gas. Now it's 2 and 2. The number of molecules are the same. So, okay, not really a big deal. It looks almost even. I would say that HCl is just one molecule that's more ordered than H2 and Cl2. It's a different molecule, a little bit more complex. It's polar, things like that. But it's either equal or negative. B, you have the same situation, except for on this one, it's going to a solid. So it is most definitely negative. It is going to a more complicated molecule, more ordered. It is going to something that is, you have fewer molecules of gas, especially, look at that. And it's going down to a solid, so definitely negative. On the C one, you're going from a solid to 3 different gases. You're going from 2 molecules of a solid to 6 molecules of gases. It is most definitely a positive value. It is a large positive value. And D is going from 1 molecule of gas to 2 molecules of gases. It's becoming less ordered, which this is definitely a positive. D is definitely positive, but it's asking you for the largest positive. And C, hands down, is the largest because on 7th levels, solid to gas, 2 molecules to 6 molecules, more ordered to less ordered. All these different reasons are why C is a larger positive value than D. All right, so that's number 7. Ari has another question, multiple choice number 13. So we pick number 13, and let's scroll down to number 13. All right. When calcium chloride dissolves in water, the temperature of the solution increases. What are the correct signs for delta H, delta S, and delta G for this process? And so I'd like to do this on the bamboo sheet. There's going to be a question like this on the test. So let's go ahead and share that. All right. So this is multiple choice number 13. So we have CaCl2. That looks terrible. Dissolve in H2O. So the first thing I would do is say, okay, CaCl2 as a solid is dissolving into a Ca2+, which is aqueous, plus 2 Cl minuses, which are also aqueous, okay? So in this situation, my delta S is going to be positive. We've gone from a solid, let me change the color so I can highlight the things. We went from a solid to aqueous. We went from 1 molecule to 3 molecules. These are definite signs of, going from more ordered to less ordered. You've increased the randomness. There's more possible orientations. Okay. So delta S is definitely positive. All right. Also, they said the temperature in the water increases. If the temperature increases, that's exothermic. If it's exothermic, then delta H would have to be negative, right? Negative is loss of heat from the reaction, right? So if that is the case, then we know that the delta H is going to be negative, all right? And now we have to look at delta G. So now we need to look at, there's not a lot of equations open to us. So this is the one I would go to. Delta G is equal to delta H minus T delta S. Now this is the part where you could have it memorized, but let's say you write it down, okay? We know that delta H is negative, okay? And then minus some temperature times delta S, which is also negative. Oh no, I'm sorry, which is positive. Haha, see, right here, positive. So you have a negative minus a positive, which means you're really going to make this a very negative number. All right? Because if you have like -2 minus, even if you said 300 times +2, right? This makes this -600, and that would be -2. No, I'm sorry, or -2 minus 600. So you'd end up with -602. It's going to be negative is what I'm trying to tell you. So delta G is equal to negative, all right? Which means this would be a spontaneous reaction. So we need to look for one where delta S is positive, delta H is negative, and delta G is negative. Okay, so let's go back and look at our test. And here we go. So we said we have to have a delta S that was positive, so it's either A or D. Delta H had to be negative. Again, that's A or D, and delta G was negative, so that's definitely D. Okay, and that was the right answer. So that's how you would solve that problem. Hopefully that makes sense. Oops. All right. Okay. Let's do a specific heat problem. And then if there aren't any other questions I have a sample problem or two that we can practice on. I thought I would just take a quick look. Okay. No, this is good. Okay. So let's do this specific heat problem. Let's go back to the bamboo paper. Okay. I forgot to check my emails just in case somebody was, and nobody is. That's okay. Okay. Let's go to a new page. And we'll call it specific heat. Let's give it back to the... Okay. So the way you solve for specific heat, Q equals M times CSP times delta T. And so if they're looking for the joules, if they're looking for heat, they're looking for the energy, they're looking for the joules. This is all equal to Q. If they're looking for the mass, they're looking for grams. They're asking how much. This is going to be mass. If they're looking for specific heat, specific, do you see that? Not just heat, it has to be specific heat, okay? That would be the occasion that you're looking for CSP. And then finally, if they're looking for temperature change, if they're looking for initial or final temperature, all right, that's pretty much a dead giveaway that you're going to be dealing with delta T. And if you guys remember that when you're solving for, if you're solving for Q, it just looks just like this. If you're solving for any of these other ones, then it's going to be Q over something. So mass is equal to Q over the other two, CSP delta T. If they're looking for CSP, it's equal to Q over M delta T. If you're looking for delta T, it's equal to Q over M CSP. So that, I mean, you're always seeing the Q is on top. always the amount of energy it was. Something else that you need to be aware of, if we're talking about specific heat, if you have, let me set this up a little bit. I don't know if I'm gonna have a picture or not. Probably not, just because I don't wanna have to create it. You've got your nested coffee cup calorimeter, right? And we've got it covered with something. And out of that is our thermometer. I am a horrible artist. Okay, and inside of here are the reactions. So we have molecules reacting with other molecules in water. Right, here's my really weak looking water molecule. Okay, so what that is telling us is that you have a reaction, and that reaction is either endothermic or exothermic. Okay, if the reaction is endo, then what's happening is the water that's all around gives up heat to the reaction. And this is heat energy. We're going to call it heat energy. Okay? Which means that this is Q. All right? We can just label it Q, as a matter of fact. This is the Q. This is where it's going. Okay? The heat is going into the reaction. Okay? The water is the surroundings. And the reaction is our system. So everything is in regards to the system when you start talking about specific heat. That means that Q is positive in this situation because, according to the system, it's gaining heat. It's endothermic, so it's the reaction's happening, it is gaining heat. A great example of this is the ammonium chloride in water. It starts to feel really cold, okay, if you start dissolving it in water. Now, the other side of this is if your reaction is oh my goodness, I didn't give myself enough space. If your reaction is exothermic, okay, and the water's all around, and in this situation, the heat is coming out from the reaction to the water. So now it's negative, because according to the system, it is losing heat. It's giving up heat to the surroundings. So now if you put some calcium chloride in water, it heats up, it dissolves that reaction. If you put sodium hydroxide into water quickly, or while you're dissolving sodium hydroxide, that gets pretty hot. If you put acid, you're diluting acid into water. If we don't ever let you do it, but if you added concentrated hydrochloric acid into water, it gets really hot. And that reaction, right? It's dissolving into water, so to speak. That's exothermic. It's giving off a ton of heat into the water. So the water is your surroundings. So you need to think about it. The reaction, this would be very similar to the, I'll use a different color here. The metal, remember when we did the metal? The metal is the same thing as the reaction that's happening, okay? It's either giving up or gaining heat. So that's something to remember when you're doing the test. Okay, so now I have a sample problem. I'm going to minimize that one. go. All right, let's take a look. Okay. All right, so we have this reaction, and this one right here contributes to the formation of photochemical smog. Very interesting. Nitrogen monoxide plus oxygen in the air gives you nitrogen dioxide. So calculate the quantity of heat released when 73.1 grams of nitrogen monoxide is converted to NO2. So looking at that, you realize, hopefully, that you are dealing with a very similar problem to 1A, where you have grams, you need to convert it to moles. Because right up here, this is delta H. This is, okay, if you are making 2 NO2, that's how much delta H you have. Okay, so if you're doing this, if you're watching this later, you should stop for a second, stop the video, and try to solve this. I kind of gave you the hints, but try to figure it out. I'll give you a moment. Okay. So what I'm going to do is actually I'm going to raise this up right here, and I'm going to show you the answer to that. All right. So you had the 73.1 grams. You divide it by 30.007 grams. They used a different periodic table, but that's fine. And that gave you the moles of NO. And now I emphasize the fact that there are you got 2 moles of NO2. And so that's how much energy is when there's 2 NO2. So you have to pay attention to coefficients. So if that's 114.1 kilojoules per 2 moles of NO, right? For every, this is what you do for moles, they cancel out. Grams, they cancel out. And you end up solving for negative 139 kilojoules. So that was pretty tricky kind of, but hopefully you were thinking about that. All right, let's take a look at the next one. Use the data in the table below to calculate the bond energy in kilojoules per mole of the nitrogen-oxygen bond in NO2. Assume that the bonds in the NO2 molecule are equivalent. Okay, that's fine. Oh, because the NO2 is probably a double bond and a single bond. And so, but that's a resonant structure. So they're both 1.5 instead of there being a double and a single bond. That's why they're equivalent. Okay, so you have the ones that are broken minus the ones that are formed. Okay, so now stop for a second. There's the data table, and see if you can do that calculation. Okay, so hopefully you stop it. And for those of you that are watching, those of you that are doing it right now, I have to keep going, but hopefully you're getting the general idea. So then you would take 2 NOs, so 2 times 607, plus your 495 minus 2 times X, because that's the one you don't know. And you would set all that equal to the negative 114.1. So you just solve for X. So there we go. Right there, 607 times 2 plus 495 minus 2X equals no. My dog is barking. I might have to go get my dog here in a second if she doesn't stop barking. So anyways, you do all that and you solve and you get 456 kilojoules. Don't forget to the fact that it's 2 times, because you're looking at 2 NO2s. So you have to, those are formed 2 times X, because that's one you don't know. Good. All right, we're cruising right along. The next one, for the reaction at 25 degrees Celsius, the value of the standard free energy, this is the delta G, is negative 70.4 kilojoules. Indicate whether the value of delta G would become more negative, less negative, or remain unchanged as the temperature is increased. So if we look at the problem, more negative, less negative, or remain unchanged, and you have to justify. So as the temperatures increase, okay. Look at this problem, all this information right here. So, and then I'll stop. So I'll give you a second to work on it. Okay. So, this is one of Le Chatelier's principles. The delta H is negative, which means that it's exothermic, which means that heat is a product, right? Plus heat, right over here. So if we increase the temperature, that's adding heat here. That's what we did say, right? Temperature's increased, yes. So we've increased temperature, which means that if we increase temperature, it's going that way. So it's going to want to go backwards. It's going to want to go back towards the reactants to establish equilibrium. Okay, which means it's going to go, it's not towards the products, back towards the reactants. Now, what that means is that it is, and you know that delta G being negative is spontaneous. Well, if we are moving back towards reactants, it's becoming less spontaneous. So it is less negative. It is not more negative. That means if it was more negative, it would be more spontaneous. And we know it's not remaining unchanged. So as temperature increased, oh, this is another way of doing so there's actually two reasons. Haha. You could use either reason. T delta S, as the temperature increases, that value becomes larger because we've already established that the S, well, we don't already, but it's positive because you went from 3 molecules of gases to 2 molecules of gases. So its delta S is positive. So it becomes a larger positive value, causing an increase in delta G, which is less negative. So I would accept either. I know that the AP readers would accept either explanation. So, but that's pretty good. So you can do it, mathematically or logistically with the Le Chatelier's. Either one is fine. Okay, last question. Use the data in the table below, and at the beginning of the problem to calculate the value of the standard molar entropy S naught for O2 at 25 degrees Celsius. You must include correct units in your final answer. Okay. So I'll just stop here then. You got to find the delta. Oops. Okay, sorry. They want the S for the O2. Now, this is not the same as delta H. You can have S naught. You can have inherent entropy in a molecule. If it's in its standard state, it still has entropy. It's not like it's 0 for delta H. So my big hint here is find that delta S first. Okay, go ahead and answer it now. Okay. So there's two parts to this question. The first is you have to bust out that Gibbs free energy. Delta G equals delta H minus T delta S. You have the delta G from right here, okay? And you have the delta H right here. And the temperature is the 298 Kelvin. So you solve for delta S first. Once you get the delta S, oh my goodness, the dog is gonna kill me. I'll be right back. Okay, I'm gonna have to talk a little bit quieter because I keep the door open so I can get the dog. So you're solving for, you're using the Gibbs free energy. Once you get that delta S, then it's the delta S. Remember, it's the sum of equations. So let me just show that to you. So you saw using the delta G, the Gibbs free energy, you found the delta S, okay, delta H minus delta G over T. You get that, and then you can plug it in over here. So the negative 146.6, well, I did the number wrong, that's fine, equals, and then the problem, if you remember the equation, 2 times NO plus O2 yields 2 NO2. And you have values for NO2, oops, you have values for NO2 and NO. You're looking for the O2. And remember, it's products minus reactants, so it's one of the second one. So it is 2 times the 240.1 right here minus the 2 times the 210.8 plus the S of oxygen. Okay, and then you're just solving for it. And then you get this positive 205.1. And in this particular equation, if it says make sure you put units, you're only getting that final point if you include the units, okay? Now, you must include correct units in your final answer. This is a 4-point problem. Now, this is what I would say. This is the stuff you have to pay attention to for AP Chem. So if you didn't include units here on the negative 146.6, that's okay. You still get the point, okay? When it says where you have to include units, you better include units. So now if you're not paying attention and you're not thinking about units and you leave off the units off both of them, well, then you're gonna miss a point. So this is why I want you guys to use points all the time. I use units all the time because then you're prepared for it. I don't want you to get tricked like that. And because sometimes it's a major deal, but it's one of those funny things about grading. Sometimes they're like, we just care that you get the answer. It's okay without the units, or different variations in the units are fine. Like the, when you have delta H being kilojoules or kilojoules per mole in thermo, that's the same thing. It's not as big of a deal. So it's kind of interesting. Well, it's interesting to me, but that's because I'm grading them. So anyways, that is one of the practice problems I wanted to show you, and hopefully you're able to get a little bit out of it. Let me know. I think I have some other practice problems if you guys want them. Of course, you're going to want them. I will post them in the thermo folder. Excuse me, I'm so sorry. I'll post them in the thermo folder, and I'll send out a message in. I will send out a message in Schoology as well, let you guys know. So that way, if you guys are looking for some more work, not work, but if you're looking for more practice, sorry, you should also be using the review books anyhow. And I tried really hard to make this test similar to the first test. And again, that it has, I think it does a good job of covering the concepts. So let me know if you have any questions. There were no other questions submitted though, but I'm just saying later, and come in and see me or email me, message me. And good luck studying. Make sure you get some rest too. All right, see you guys in a couple days. Bye. Oops. All right. Bye. See you guys in a couple days.